and today I will speak about the relation between volume geodesic distortion and curvature in sub-Riemannian geometry. So I will start with some motivation and introduction. So I will try to explain what are some motivation for studying this problem, what happens in the Riemannian case, and then I will discuss the generalization to the sub-Riemannian one. So the work I will speak about is a joint work with Andrea Grosov, that is here, and Elisa Paoli, who is a former PhD student at SISSA. And so these are the two main references I will speak about. And so let me start with the motivation. So to start with, since there is Ricci curvature in the title, I wanted just to relate this notion with the volume. So one basic construction that is also a possible way of defining Ricci curvature in Riemannian geometry. So we have a Riemannian manifold. We fix a point on the Riemannian manifold and a unit tangent vector. Maybe I can use this to a unit tangent vector V, and we consider the geodesic gamma of t associated with V, so with initial vector V, and along this geodesic we pick a frame, an orthonormal frame at 0 that I call here E1 En, and we move it along the geodesic via the exponential map, and we are building what are classically called Jacobi fields. So if one computes the volume in the sense of canonical Riemannian volume of this parallel top defined by this frame along the curve, what you get is that the volume of this object is 1, of course, at 0, because the frame is orthonormal. When t is positive, it is no more orthonormal a priori, and the first order correction term at order t square is the Ricci curvature of the manifold. So this is just to make brief recall. To make a link, since I'm not really speaking in this talk about Laplacian, I will still make a link with the curvature and Laplacian that goes as follows. So let us define the Laplacian on a weighted Riemannian manifold. So we fix a Riemannian manifold and a smooth measure. So I call delta mu the divergence with respect to the volume mu of the gradient. So if we fix mu as the canonical Riemannian volume, we are defining the Laplace-Beltrami operator on the manifold, and we are interested in the fundamental solution of the heat equation associated to this operator. So delta mu. So one can use classical results, and one thing that one can do is to relate this, let's say, Laplacian associated with an arbitrary smooth measure mu with the Laplace-Beltrami, that is this one, and one has a first order correction term that rides through the gradient of the function psi, such that mu is written as exponential of psi volume of G. Here vol G denotes the canonical volume. And so one can use classical results and get this expansion for the its kernel, so small time asymptotics, on the diagonal. Now here I'm just looking on the diagonal. So we have a constant over t to the power n square, n divided by 2. So n is the dimension of the manifold M. And the first order term here contains the scalar curvature, that is the trace of the Ricci tensor I introduced before, and two other terms that contains information about the function psi. So that somehow relates, if you wish, this is the one point I want to stress in the following, an interaction between the measure and the metric. So this somehow motivates the study of interaction between dynamics, the geometry, and an arbitrary smooth measure on the manifold to get out some invariant that maybe could appear in this expansion for the general case. So this would be final conjecture, let's say. So to approach the object we are going to study, I will put myself in the following setting. So we fix again complete connected Riemannian manifolds. You can think, if you wish, also to a sub-Riemannian one. And we fix a smooth volume form on M. And for a bounded measurable set with a finite measure and positive measure, we want to build the set of t intermediate points between omega and x, where x is a fixed point. So what we are doing, I'll try to explain on this picture. So we have a set omega here, a point x, and for each point in omega, I'm considering, let's say, the unique geodesic connecting x with the point of omega. Of course, this is not possible to find for each point a unique geodesic, but for almost every point, this will be the case. So this is what happens in the Riemannian case. If you wish, since we are going to look things from the asymptotic viewpoint, you could think to have this point y to be regular value of the exponential map, and omega just the image of a small set A in the tangent space. So in this case, there is no problem. And what we'll be interested in, let's say one question that one could address, is consider the set of t intermediate points, so point at time t along geodesic connecting x to omega, and to study the behavior of the measure mu, so that is somehow external, of this set. Just to understand why it could be interesting to go through this question in the sub-Riemannian case, let me just mention. So of course, if we do this computation in the Riemannian case, we look to the main order of this object, mu of omega x t. This will grow as t to the power n, where n is the dimension of the manifold. And then we expect, of course, higher order term to be curvature terms. And I will go to this later. What happens in the sub-Riemannian case? So for instance, if we take already the simplest case, the Heisenberg group, that also Antonio mentioned just in the talk before. In this case, one can compute, so it was proved for the first time in the paper of Nicolas Julier in 2009, that if you look to this expansion, indeed in the paper it proves more, but it follows that the measure of a set contracted along this geodesic goes as t to the power 5. So this 5 is not neither the topological dimension of Heisenberg group, that is 3, neither the metric dimension, so the house of dimension that was mentioned this morning from Emanuele. And so it's another, let's say, dimensional invariant that we could think to something associated with the geodesic structure, let's say. So in what follows, I will try to motivate why this 5 appears here, and go further in the expansion of this quantity in T. So find higher order term. Good. So let's go back to the general setting here and have a look to what I'm actually going to study. So if you want to compute this quantity here, and we write the set omega x t as the image of the exponential map at time t of a set A. A here is just a subset of the tangent space at x. We make the change of variable, and we can write this integral as the integral on the set of parameters A of this pullback measure of mu through the exponential map at time t. So this is the object I will study. So indeed, study the asymptotic of this family of measures. So this family of measures that I denoted here as x star x mu is a family of measures that lives on the tangent space to the manifold. That here I put in a vertical sense to think about the fiber, but it should be tangent. In a while, the same picture, we have a cotangent space, so it will be vertical. And so the picture is as follows. We are taking a small set, a small neighborhood of initial vector v, and we are considering this set here that is contracting through x. Or in the same way, I am pull backing the measure mu on M to the tangent space. And of course, if you want to write an expansion of this family of measure, we should fix a measure on the tangent space to compare it. Okay, so let us start with the Riemannian case and to write the general formula. So let us first consider the, so we start to compute in the case that mu is the Riemannian volume and see what happens. So notation is as before. So GIG is the coefficient of the metric, x with exponential map, and volume, the Riemannian volume, I use this coordinate formula, and through this and the classical formula expansion of the metric in normal coordinates, one could get this expansion. So the expansion of the determinant of the metric along a trajectory, and indeed we get exactly what we had before. So this somehow connects with the first and second slides. And using this formula, we can compute the pullback through the exponential map of volume. So we want to compute this object here, and we use the formula that is here. In general, when you have to compute the pullback of n form times a function, you just compose your function with the diffeomorphism, let's say, and then you pull back the form with phi, and so we get this, the function that is the square root of the determinant evaluated on trajectory, and the pullback of the, let's say, Lebesgue measure on the manifold. If we use we write things in normal coordinates, indeed in normal coordinates this exponential map writes as an identity, and so this object is equal to the x1, the xn, but more intrinsically, we can think to this as the induced volume on the tangent space. It's simply the volume defined by the metric on the tangent space. And so we plug in our expansion here. And another things I will do, since I was interested in the exponential map at time t here, I use the homogeneity of exponential map at time t of v is nothing but exponential map based at x at tv. So when you compute pullback, you get a t to the power n that gets out. And you put all things together, and you have this. So this object, so when you compute this pullback of the Riemannian volume, you have this formula. It is, so t to the power n, the expansion we had before that contains Ricci curvature, and this induced volume on the tangent space. So now that we have this formula, we can easily get the one for a weighted Riemannian manifold when you fix another smooth volume mu. If you write mu as before as exponential psi times the Riemannian volume, now what we get more than before is simply this term here. So the exponential of this function psi along our trajectory gamma of t, that is our reference trajectory. So I wanted to manipulate a little bit this formula to make here in the right-hand side appear the volume induced on the tangent space by mu. So to have in the left-hand side and right-hand side something that is related to our external measure mu. So what I do is use a classical formula, so fundamental theorem of calculus. So write our function psi along the curve gamma of t as its value at the origin plus integral of its derivative. That is here. And so when we plug in this formula there, we will have exponential of this quantity times exponential of the integral. And I will put the exponential of psi together with the volume to build this object that is nothing but the measure induced by mu now on the tangent space. So it's simply multiplied by a constant. And we end up with this formula here. That is, let's say, the general, the formula for the pullback of a general volume mu in the Riemannian case. So maybe let me just comment a little bit. A first thing that is interesting maybe to write down is the following. So we have this function that here I denoted rho that is related to the function psi. So I recall that I am fixing mu as exponential psi volume of G. So everything that is related to mu in the formula appears through to the function psi, of course, now. And so there are two interesting things to say. The first one is that in this formula we have somehow split the contribution of, or let's say isolate the contribution of the volume in this term. So the only things that affects the asymptotics, where mu affects the asymptotic, is here. Okay, because this t to the power n does not depend on the volume. This parenthesis, together with, if one wish, even the small o of t square, also is consequence of the first expansion. And this, if we change this, indeed, it just change a constant, so it does not really change the asymptotic. So what I'm saying is that the volume is affecting the asymptotic only here, in this term. Of course, this term is written in integral term, so if one develops this quantity, one would have this element at each order. But still, it is isolated here. We know how to treat it. The second one is that we can somehow write, let's say, an intrinsic formula for this quantity that does not involve the function psi, as follows. And I write down, since it's going to appear a similar formula later. So if you want, rho of v can be written in this way. So rho of v could be, I write this way, put this measure here. Could be thought as derivative at t equal to 0 of log t minus n of this object. So I'm just using this formula to write an identity for rho. So a priori, you see, this object makes sense without using this, and defines somehow this invariant here, just starting from the measure mu. And so he's saying that you take your measure, you take its interaction with the dynamic, and you compute kind of a log derivative where you remove the main order term. So this is just so it could seem a tautology here, but I stress that here you have the derivative at time 0, and here you integrate this object along the trajectory. So it is not immediate from this formula that one has this. I mean, it goes in this direction, but not immediately in the other one. Okay, so just to connect things with the formula with the Laplacian, let me notice that if one develops this integral here and this exponential, one would get this formula here. So at first order, you get your rho, and at the second order, you get these three terms. Okay? Because if you look here, of course, when you put t equal to 0, you have 0. And then when you compute the derivative of this integral, you get rho. That will appear at order t. And at order t square, you will get the derivative of rho and rho square. Okay? It's a simple Taylor expansion of this at 0. And what is interesting is that if you compute the traces of the three objects, you have this here, you get exactly the three coefficients that were appearing in the order 1 term of the heat kernel expansion. So what we are saying is that the object appearing in the second order term expansion of the volume indeed are the coefficients, the invariants that determines the first order term of the heat kernel in the Riemannian case. So this is what happens. So here are just two formulas for rho squared and the derivative of rho. Okay. Nice. So now the second part of the talk, and so the generalization of this to the sub-Riemannian case. So indeed, in our work, we treat not only let's say sub-Riemannian case, but let's say Hamiltonian flows associated with quadratic Hamiltonians. So of this form that are associated comes from optimal control problems of this form here. So affine optimal control problem with a drift and with a cost that has the form of a kinetic energy minus a potential. So here x0 and xi are smooth vector fields, and q is a smooth function in this setting. So to simplify what follows, I will just stay in the sub-Riemannian case. That means for me to put the drift and the potential to 0. Because if you look, indeed, the first equation says that your tangent vector to your trajectory is in the span of this. So this equation is just saying that your tangent vector belongs to the span of x1, xk. So x1, xk is just my distribution, and this quantity here, this kinetic energy, is nothing but the energy of the curve. Indeed, jt of u can be written in this way. With a square, yes. Thank you. And of course, I will assume that Ormander condition holds everywhere, so that the Lie algebra generated by these vector fields is maximal. It's maximal dimension at every point. So so what do we do to write down an expansion that is similar to the previous one? Here, since we have Hamiltonian flow, what is natural is to replace things that are defined on the tangent space to things defined on the cotangent. So formally, it's not difficult because since we have an Hamiltonian H, we have its Hamiltonian vector field that writes in this way in coordinates, and we can simply consider the flow associated to this Hamiltonian vector field that is here and project on the manifold downstairs, and this will define our exponential map at time t. So we are fixing initial point x, and we restrict this to the fiber at the point x. So, of course, the two approaches are equivalent in the Riemannian case, but in this setting, this is somehow the natural one. So, from the formal viewpoint, in my theorem, I will just replace exponential map with this exponential map. So, let me just say that things are not so simple, because, for instance, I put this picture just to see a nice picture at some point. Just recall that in the sub-Riemannian case, since you are dealing with an Hamiltonian flow that now has this form, so where is it? Is a sum of squares. The Hamiltonian flow, you know, satisfies the property that the flow stays in the level set of the Hamiltonian. But now the level set of the Hamiltonians are not compact in this case. So the unit set of initial condition in the Riemannian case is a sphere, here is a cylinder. And so when you look to the exponential map, this is no more a local diffeomorphism. So this is the set of initial condition, geodesic, let's say, parameterized by length, and this is the image through the exponential map of this set. So it is not let's say, so immediate to generalize this, even if from the formal viewpoint I will have the same expression, let's say. To write things, let me just recall that we are going to pull back our smooth form mu on the cotangent space now, because I'm using this cotangent version of exponential map. And so what is the measure on the fiber I will use to compare? It is just the dual element to mu hat x on t star xm. Indeed, what we had, I recall, we had the smooth volume on M. The value, let's say, if you look to this as a top dimensional form, the value of this at a point gives you a form on the tangent space, but the vector space of n-dimensional forms on a vector space has dimension 1. So you can fix its dual element and fix this as a representative to write down the formula when you look to this in the cotangent space. So this is the result for the general case. So let's see what happens. So we fix now a geodesic that is so the image through the exponential map of an initial condition that now is no more a vector v, but is a covector lambda. So lambda stays in the cotangent space at x. And we have two assumptions. So this geodesic should be ample and equiregular. I will speak about this later. If these two assumptions are satisfied, then we have this asymptotics for our volume. So what do we have? We have a constant c lambda times t to the power n of lambda. N of lambda is an integer. Exponential of the integral of rho, so the same expression as before, where now rho is indeed, you can think to be defined indeed by the analogous formula that you have here, times a smooth expansion where the first order term t square is the trace of an operator r of lambda that is a symmetric operator that plays the role of curvature. So indeed, let me recall you what happens in the Riemannian case. So in the Riemannian case, the constant is 1. The integer is the dimension of the manifold. The operator is here, is defined on the tangent space, and is just the Riemann tensor contracted in the direction of the geodesic. So when you take the trace, you get the Ricci of it. And our rho was simply the gradient of psi. So where you identify the vector and the covector by the isomorphism given by the metric. So that's the situation. And in general case, so you have this r of lambda is a symmetric operator that is defined only on the distribution. What happens is that, as before, what is interesting from my viewpoint is that the expression that is here in the parentheses is, like in the Riemannian case, a full expansion, so even the small o could be determined, and depends only on the dynamics. So it's like kind of curvature invariants, even higher order a priori. What in Riemannian case are derivative of the Riemann tensor. Here you could go further, but depends only on the dynamics. So finally on the Hamiltonian H, if you wish. The only point where the measure mu enters is here, so in this function rho. So this permits to easily understand what is going to change if we change the measure. And what is the constant and the integer? So I'm going to tell you soon. So indeed, in this final part, I will just try to say what are the different objects here, and I will do this also explaining the two assumptions. So to say what are the assumptions and to explain what is this n, that is the first interesting object that appears, because indeed the constant is just a constant. I need a couple of definitions. So I will repeat a construction that is similar to the one that presented Emmanuel this morning about the flag of the distribution, but here is a flag that is built by a derivative along only one direction, the direction of our trajectory. So we fix the first element of the flag f1 is our distribution, and the sequence of subspaces are given by the previous one plus what you obtain by differentiating elements of the previous one with t, that is an admissible extension of your trajectory. So you fix your trajectory and you fix a smooth vector fields that along the trajectory is gamma dot, and you make derivative only with this guy. You have an increasing sequence of subspaces, and you can take the corresponding dimension of these subspaces. And so we will say that our trajectory is ample if at some point this increasing sequence of subspaces fill the tangent space. So it's kind of bracket generating condition, but along the trajectory. And we say that it's equiregular if this dimension of this flag is independent on the point on the trajectory. So I say sometimes these are kind of micro-local bracket generating, because they are not local in the sense that concerns a neighborhood of a point, but the germ along the curve. But it's not micro-local in the same sense of the micro-local analysis. Let me say that if we have these two assumptions, our trajectory is not abnormal for those that are interested in the abnormal geodesic, but still, and there are no conjugate points for small t, but still there are a lot of this. Indeed, you can prove that the set of initial condition, initial covectors, such that your trajectory is ample and equiregular is a non-empty open and dense set in the whole T star M. And if you fix a point, then the same, you have a non-empty open dense subset in the fiber that are ample. Because a priori, if you are in a non-regular point of the distribution, then you have no hope to find equiregular trajectory in this sense. If your distribution is not equiregular, then of course it will be difficult, because even the first layer will not have constant dimension. But still you have a lot of these objects. So this is kind of generic condition. And now that we have this, I can tell you what is this n of lambda. So we fix our trajectory. We have k1, km are I recall you the dimension of fi. So ki is the dimension of fi. And I am assuming that this object is independent on t. So they are just numbers. So the constant C lambda is just something between 0 and 1 and depends only on these numbers. So I'm not writing the explicit formula, this is not really interesting. And on the other hand, this integer n of lambda here is written in this term. So as a formula that looks like the one for the Hausdorff dimension that this morning Emmanuel wrote, but where we multiply here by odd number and not for all integers. So we have the difference, so the number of dimensions that we are adding at each step when we differentiate, and we multiply by odd number. So just to understand the simple case, so the contact case. In the contact case, we have an odd dimensional manifold. So the dimension of the manifold is 2n plus 1. The distribution has dimension 2n. And of course, so one can see that for every geodesic, in this case, the Grove vector is the same. All trajectories are ample and equiregular. So this is a setting where no need to specify our previous assumption on the trajectory. And so when you apply this formula, so you have 1 times k1, so 1 times the dimension of distribution is 2n, plus 3 times 1. That is the difference between k2 and k1. And so it's 2n plus 3. And if you do this in the Heisenberg case, so in this case, this g of gamma will be 2, 3. And so this n of lambda will be exactly the 5 we had before. And so this is a number for every contact structure. How much time do I have still? 20 minutes. Okay. So good. So now a few words about this invariant row. So I wrote again this somehow intrinsic formula for this invariant, but that is not telling us very much about it. So indeed, a few properties of this invariant could be said. The first one is that this row can be seen as a divergence of our external mu along one admissible extension t. But indeed, we have to be careful. There is a correction. It cannot be really written as a single divergence, but it is a difference of two divergences. The first one is some external divergence, so divergence with respect to mu, minus a kind of, I would say, internal divergence with respect to some volume that I call here omega, that is a volume that depends on the trajectory. So it's something that could be defined along the trajectory. In the Riemannian case, this object here is simply the restriction of the Riemannian volume along the trajectory. But in this general case, this is trajectory dependent, let's say. It is not the restriction of a big object along the trajectory, but depends really on our curve. So it's somehow a divergence. That is what one could naturally think about when you think about interaction with about a flow and a measure, divergence. But there is, let's say, a non-trivial point. And what is interesting is that it could be proved to depend only on a kind of nilpotent approximation that is defined, again, only along the trajectory. So I'm not going into these details because they are quite technical and I have no time. But in the same way as Emmanuel this morning defined the nilpotent approximation of the structure in a neighborhood of a point, so a kind of local, depending on the local structure, one can define a micro-local. So looking just what happens along the trajectory. So indeed using the flag I introduced instead of the flag defined by the distribution. And this quantity indeed depends only on this. So it's a kind of first order invariant, let's say. It does not depend on the property of the point, but the first order in the sense of this nilpotent approximation, and is a rational function on the set where it is defined. So a rational function on covectors that defines ample and equiregular geodesic and is homogeneous of degree 1. So it comes at the first order and is homogeneous of degree 1. Is quite natural. And just to explain you what is in a natural situation, so again, contact manifold. So contact manifold we have seen a few times today. So the distribution is the kernel of one form, omega, and so we have a metric on this distribution, and omega, the differential of omega on the distribution defines a symplectic form. So this guy here is not degenerate, and we can define the contact endomorphism J by this formula. It's a classical object when you deal with the contact manifold, and the quantity rho of lambda can be computed in this way. So it's simple. Is the variation of this contact endomorphism along the trajectory. So you compute the derivative of the log of this quantity. If you fix a structure where j squared is equal to -1, and indeed I forgot to say that here as a volume I am fixing the natural volume that is defined by the pop volume in this case, that is equivalent to take the Riemannian volume associated to the normalized Rib vector field. In this case, for all structures such that j squared is -1, this rho is 0. Okay, so now I want to say a few things about the other term, R of lambda. And to do this, I will recall a construction that we use to define a curvature in this sub-Riemannian setting. So I will try to avoid technical points, but let me just explain the main ideas. We have always our trajectory here, starting from x0, our gamma of t, and we define this function here that I am calling geodesic cost. So ct of x is -1 over 2t, distance square from x to gamma of t. X you can think to live in the neighborhood of the point x0. And if the trajectory is ample, so we ask this assumption trajectory, then you can prove that this function ct of x is smooth on an open set U inside this 0 epsilon times the neighborhood of x0. So you have regularity of this function for t positive. This here is very important that t is positive, because in general in sub-Riemannian geometry the function y that associates, let's say, let's call this point x0. So this function here is never smooth on the diagonal. So it's never smooth on at x0, this function. So indeed, what you cannot do is to recover, let's say, curvature from derivative of the distance computed on the diagonal. That one could do in the Riemannian case, since d squared is smooth on the diagonal. In this case, so what you are obliged to do is to have some conditions such that this function is smooth for t positive, and then what we will do is to differentiate this family of function that depends on t for t positive, and then takes the limit when t is going to 0. So to compute derivative, we have to be far from the diagonal, and then we can take asymptotics. That is more or less the idea here. So another thing one can show is that if one takes the derivative with respect to t of ct dot, so ct dot here denotes just the derivative with respect to t of our function ct, this function here has a critical point. Indeed, here there is an error because this quantity is 0. This is 0. If you remove the dot, is correct, or you should put 0. I'm sorry, there is an error. And so, as such, as a family of function, this one that has a critical point at x0, then you can define its second differential independently on metric structure or coordinates. And this family of quadratic forms, when you restrict to the distribution, now you can use the metric, the final distribution, to build a family of operator, symmetric operator on the distribution. So defined this way, q lambda of t is a symmetric operator defined on the distribution that is just the unique symmetric operator associated with the quadratic form action of ct dot, if you wish, or second derivative of ct dot. And what we proved in 2013 with Andrei and Luca Ricci is that if the geodesic is ample, then you have this expansion. So this q of lambda that is singular of order t squared has a Laurent expansion of this form. So the fact that it has a pole of order 2 should not be surprising, because if you remember, I can write it here. Ct of x is minus 1 over 2t distance square x gamma of t. So of course, when you take a derivative with respect to t, you will have 1 over t squared. But indeed, a priori, it is not clear that this guy has order t minus 2. Could be much worse a priori. The fact that it's t minus 2 comes from the fact that you take restriction. So this is very important here. And so we are extracting somehow invariants from the derivative of the distance along the trajectory. And we have a first operator, or matrix, if you wish, E of lambda, and a second one, R of lambda, here in this expansion. So what are these two objects? I of lambda is bigger or equal than the identity in the sense of matrices or operator, if you wish. And its trace comes out to be our n of lambda, the number we had before, when the trajectory is equiregular. And R of lambda is exactly the object that comes out in the expansion of the volume. So it's a curvature operator in some sense, or could be treated as this. So just to say a few things in one example, or maybe two, in the Heisenberg group that I mentioned before. So it's a contact structure where you have this invariant, left invariant structure where you have this orthonormal frame for distribution, x and y. Every trajectory is ample and equiregular with the Grove vector 2, 3. And one can determine this expansion, even if I recalled you that this distance square, when you compute here, I wrote along to geodesic, is not differentiable a priori. So if you take two trajectory and you write the distance, you compare the distance at time t here, at time s here, this function is not even C2 at 0 in this case. So you cannot really expect to compute derivative at 0. You cannot write Taylor expansion at 0. But you can compute, in this case, even by hand, the expansion. And if you write things in a nice basis, so in the distribution, since you fix the trajectory, you can choose the derivative of your trajectory, and it's orthogonal. You can write matrices for E of lambda and R of lambda. So E of lambda has eigenvalues 1 and 4, and so the sum is 5, is the n, indeed, the trace of E. And R of lambda is a curvature operator somehow that is diagonal, has a 0 in one component that is associated with the fact that we have homogeneity. So in the direction of the geodesic, we have always 0 curvature. And it has this expression here, hz square, along in the other direction. What is hz? Hz in this case, I'm not finding this object I wanted. Hz is the initial parameter of the covector that is saying how much our geodesic is going up. So the initial covector lambda is hx, hy, hz, and so the hz is related on how much this geodesic is going up here. So it's kind of, when hz is 0, we get straight lines on the plane that have curvature 0 somehow. And when you have hz different from 0, we have spirals that have somehow positive curvature in this sense. So this is what happens in the Heisenberg case. We can compute it in general for contact manifolds. I just wrote the expression here. Is quite nice and written in terms of a connection, a canonical connection that we can define on a contact manifold that is called the Tanaka connection, generalization of a Tanaka-Webster connection for CR manifolds. Is a metric connection but not torsion-free. So it has torsion. And one can associate with these two tensors, Q and tau, that are defined this way. Simply, you can think to this two tensor in this way. Tau is saying if rib is a Killing vector field, and Q is saying if your structure is CR. So if both are 0, you fall into the class of Sasakian structure. For those that know what does it mean, and you have this expression, so that gives you somehow an expression. And just to finish, let me say that so with this machinery, what one could expect for now is to study this quantity mu of omega x t, and to have bound on the asymptotic for small t. One could be interested in getting bounds for all t, global bounds in time. So in this case, say we are quite sure that these invariants are not enough. One should go further in the expansion and bound next term. But still, do you have 2-3 minutes? No? Okay, but just to finish, just to say that these computations were useful to prove also something, not really directly by the previous formula, but to present some result. We were able to prove through this study a version, for instance, of Bohnemeyer's theorem for contact manifold. A version for contact manifold of dimension at least 5 with this formula. So dimension 2d plus 1 with d bigger than 1. And if we have bound of these two quantity. So now reach of nabla and R of nabla are curvature associated to this Tanno connection, and Q is the operator I introduced before. If we have these estimates with this inequality, then you can prove that the manifold is compact with this bound on the diameter. So the first one is a kind of partial trace condition, because we are removing one part of the Ricci, and in dimension bigger than 3, so when this holds, this result was known just for tau and q equal to 0. So this curvature stuff gives something, not a lot. And to go back and to finish, to go back to this story of Laplacian, what we would like is to have an asymptotic on the diagonal of the heat kernel of this form. So we know the order on the diagonal is the Hausdorff dimension, Q of x, in the same notation of Emmanuel. And what we are interested is in this object here that I call kappa. So natural conjecture is that this kappa is a function, some function, of the trace of our R of lambda, some derivative of rho and rho square, that are the first term that are appearing. And this can be verified through the known result in the three-dimensional case for contact structure of dimension 3, because I computed this for the pop volume in a previous paper, and so you can check that indeed this is true. But let's say in general is completely open, and is somehow one question that motivated our study. So I thank you for your attention, and I stop here.